Hey everybody, welcome. This is GP. I work as a data scientist at Accenture. And today we are going to talk about deep reinforcement learning in machine learning. Just to give a little bit of background about myself, I've been constantly rated as a data science and machine learning and deep learning influencer from the past few years. And I contribute a lot to the AI research community in terms of research papers and stuff. So I published around 400 research papers on AI before, and also published a couple of books on big data analytics and machine learning. And today we're going to talk particularly the reinforcement learning technique in machine learning. And next slide, please. Okay. So as we see here, the trends and the reinforcement learning is gaining the momentum. And the artificial intelligence has always been there for many years. It began like in 1950s, and then later the shift was trending towards the machine learning in the 80s and 90s. And then there was also symbolic representations of artificial intelligence. And then there was rules-based systems to set up different types of rules, how to encode all these millions of rules and then run the programs so that they could kind of feed the common sense to the machines. And that was the objective, is basically to power the machines with common sense through rule-based systems. And further, they leverage different types of techniques like machine learning. And slowly, if we start seeing the trend in somewhere in 2000, the reinforcement learning technique has begun. And that's where it has made a significant and radical improvement. And it is the most promising technique in the machine learning today that gears towards what we call AGI. This is basically artificial general intelligence. What we're trying to do is we're trying to create something similar to human brain. So basically, if we take a look at human brain, the human brain is powered by 87 billion neurons. And all of these neurons are connected to different synapses, and then they power the chemical signals and transmit them from synapse to another synapse through the neurons. So there is a set of neurons that work as the input layer, and then there is these synapses that work as the hidden layer in the middle of the neurons, and then it produces the outcomes, which is the output of action to perform. And that's the output layer of the artificial intelligence. So it not only we are moving here from the knowledge-based systems. Basically, knowledge-based systems just performs what it performs, but it cannot make the dynamic decision. If we see the human brain, there is, despite of so many 87 billion neurons, there is an emergence of a unanimous decision that we want to do this at this point of time. That decision is basically an action that's triggered by the collective intelligence of all these neurons that are networking with each other. And that's what we're trying to do with reinforcement learning. And reinforcement learning is the most promising technique that's getting towards AGI because it does not need historical data sets. If we see most of the machine learning techniques take the labeled data, there is so much of tsunami of big data. So we just take the big data and turn it into labeled data and then convert it and then feed to the machine learning so that the machine learning just picks up the signals from the pile of data, and it produces the outcomes based on statistical methods and mathematics, and then it gives the decision for the businesses or the enterprises to kind of provides that decision power as to where they would like to go. Like it could be advanced financial forecasting, or it could be supply chain management, it could be retail industry, or it could be even cybersecurity to find what is spam, what's not spam. So there are several statistical techniques that runs through this pile of data to produce these type of outcomes. So that's what the conventional machine learning does. Basically, it takes a pile of data and then prepares the rules, and prepares the program, and produces the outcomes. But reinforcement learning, it does not require historical data sets. Because most of the time, let's say that we have a rover that's going on to Mars. It has to land. So basically, it does not know the atmosphere, and it doesn't have any prior knowledge of how the planet is going to look like. And so basically, when it lands, it needs to know the path. There are several paths to land. So that's where there is no data. Because even if you have to go onto a mountain and we drive on a car, and then we haven't seen that mountain before, so how do we drive to get there on a steep mountain? So there are several scenarios where we don't have data to make a decision. And that's where the dynamic emergence of decision comes, which is the action. And slowly towards 2002, we started seeing a tremendous leverage of statistics with Bayesian networks, and then support vector machines, and neural networks. All have picked up the momentum, and slowly we started moving in the past decade towards something called deep learning. The deep learning has thousands of layers of these neural networks. It's not just something that we just run through a simple machine learning technique to produce the outcome. So it takes the machine learning to completely to a next level. For example, like we want to do drug discovery. We want to invent something to cure the rare diseases. So because we have to explore the genomics, understand the DNA, and we have to advance the medicine, or we have to advance the neuroscience. All of these things require so much of data, and it requires powerful neural networks that can understand and interpret the data and then explain the patterns of the data. And that's what the neural networks does. So the deep learning takes it to the next level. So here we are seeing, this is basically a treasure trove of MIT technology reviews, research papers that have been downloaded. And basically, we did the analysis to see the trend towards the reinforcement learning, machine learning, and deep learning. So the industrial trends and the research trends show here, basically, the third and final shift has been the reinforcement learning. We have seen the trend from the symbolic-based machines, and then knowledge-based machines, rule-based machine, and then machine learning, and then now towards the reinforcement learning. So what does this tell us, the trends here? So basically, the research community has ignited the world by powering the artificial intelligence through reinforcement learning. And if we start looking where did it pick this much momentum? What did we achieve to say that it has actually picked up the momentum? So DeepMind is basically a Google's company. And this DeepMind has built a completely autonomous reinforcement learning called AlphaGo. So this AlphaGo does not have any data at all. It doesn't have any historical data sets at all. It basically runs everything through Monte Carlo search algorithms, which are totally built by the reinforcement learning. And so for example, when this AlphaGo was trained with reinforcement learning, and it has actually defeated the world champion of the Go. The Go is the most ancient and the most complex game, which requires intelligence to make decisions, to make moves at the right times. And it's something that is done through humans because the humans have the intelligence to make these moves at the right times. But DeepMind has trained AlphaGo to do this, basically leveraging the policy networks and gradients, states, actions, and then it performs all of the moves itself with a 99.8% winning rate against any other opponent. And it has also defeated the European Go champion at 5-0. And it has also defeated a number of other human professional players as well. And how it does it, it doesn't have any data. Like, it doesn't know, like, okay, this is how either the chess is played or a Go is played, so that it has the intelligence to understand that. No, it doesn't have any such historical data. It just works on the fly and picks up the moves. It calculates so many millions of moves before a human can proceed for the next move. So it knows what move it needs to make. And that is powered through reinforcement learning. So let's take a look at the DeepMind's AlphaGo neural network training pipeline and reinforcement learning architecture. So basically, I picked up this from the research journal Nature. So here it shows the different rollout policies set out here and different reinforcement learning policy networks, value networks, and it not only envisions the human expert positions, it also calculates itself several moves before the human can actually make the next move. So this is where we are moving towards the AGI, Artificial General Intelligence. Artificial General Intelligence is expected to power a lot of explorations on new planets, like going to Mars and explore something without any historical data set. Understand the climate and adjust to the surface and the gravity, and without any navigational maps, it can figure out how to navigate in a specific landscape. So basically, MIT Technology Review has downloaded around 16,625 research papers to analyze the trends on the artificial intelligence, machine learning, and reinforcement learning. Basically from 90s through 2018, and we started looking at different trends on the traditional neural networks in the 50s, and then followed by the symbolical approaches in 70s, as I was mentioning a bit earlier. And then the rule-based systems in 80s, the support vector machines in 90s. And neural networks have been very popular for a couple of decades, from up to 2000. They are highly leveraged by a lot of corporations and enterprises for submarines, or it could be any industry, space exploration, or it could be retail, supply chain, and a number of other industries have implemented the neural networks. So here, I would like to give you an example of solving a problem with reinforcement learning. So this is the MIT technology algorithm for solving the deep traffic. So basically, so here we are seeing a Bellman equation, and we are applying a deep Q learning, reinforcement learning technique. So the way that this was implemented is through crowdsourcing. Basically, because there is no single solution to solve deep traffic, there are a number of solutions to reach the destiny and to optimize the path. So on a multi-lane freeway, there are different cars going on, and what's the most optimum way of getting from point A to point B through a deep traffic? So how do we do that? So that's what this algorithm does for the reinforcement learning to solve the problem. And the good thing is, because it's collective intelligence and we have gathered this through crowdsourcing, there are 24,000 entries for the competition. And there are around 572 millions of crowdsourced and optimized DQ and hyperparameters that are provided to produce the most optimal path for solving the problem. And a single person couldn't train. It's a 96.6 years of reinforcement learning training on the deep traffic. And all of that has been achieved. And that shows the most optimal path with a optimized hyperparameter configuration. So there are problems like this that can be solved through reinforcement learning. Yes? We're talking about changing the tires? Okay, the changing the tires, there's a different thing for NASCAR, for example, right? So,
You're talking about a solution for,
no, this is not about changing the tires of the cars. This is about deep traffic is a traffic problem.
That's not the optimal traffic, because we are not being efficient. I mean, it's for a game, but not for a real car. That's what I mean.
So basically, let me give a brief background of this problem, what we are trying to solve the problem here. So when you have a multi-lane freeway,
Thank you.
so you have several cars going, and there is so much of space. And the traffic is not really leveraging this space in the traffic, because people either tend to go either on the same lane, or they just don't know. Even if they find some space, some people don't try to get into that space. They try to stay in the same lane, assuming it may not get better if they're going to change the lanes, right? So, but what this does is it finds all the traffic spaces to the destination, not just the next lane or next mile or something. So if you're getting point A to B, what's the most optimal way of getting there? So it calculates all that, and it tells you can actually change the lane to the right and then keep going. And then again, get into another lane and so on and so forth. It gives you all these possibilities which we cannot envision with normal driving. So that's where this helps to actually reduce the traffic, because traffic is a problem. Like, I mean, in Los Angeles, if you're going on 405, it's always like stuck. I mean, it never moves. It's like you see like so many lanes, but we can't just really get into another lane. So, but is it really the problem of the traffic, or are we not leveraging the space where we can actually get into the traffic and get to the destination point? So that's what this is looking at, trying to find the most optimal path and try to get there. Again, for example, like there's also a travel salesman problem. The travel salesman problem is also like a person has to go and basically reach a destination. So what's the most optimal path? It can be applied to travel sales problem as well. So there are several examples that reinforcement learning can be applied to. I'm just taking some of the most popular and common techniques that have been applied highly successfully, and where we can actually see the results with researched results, because in other instances, we don't have much data that we can kind of display here for the demonstration purposes to see how it can basically help us to solve the problem. So this is an example for it. And also, as I mentioned to you, DeepMind also has applied it on AlphaGo. There's also in other places like, for example, arcade game learning environment. That's another environment coming from DeepMind. And there's also a physical engine for Mojoko environment that solves different problems, like could be a nuclear reactor, it could be molecular dynamics, it could be any problem. It doesn't have to be necessarily a traffic problem. But in this case, we're just talking about the traffic problem. But I can provide several other research papers. If interested, please contact me later after the conference on a specific problem, and I'll try to provide some solution. Yeah, please.
You have problems that have consistency, where there's a path that is optimal, and you're using that same path. But when you have paths that are not optimal, where there is an element of luck, or where you have inconsistency in set paths, say gambling, or say something else, where your paths are not, then reinforcement learning may not necessarily be an optimal situation because there is inconsistency. So your reinforcement may not necessarily be that chosen path. So what happens in that?
So it is much similar to actually based on the intuition of the human brain. So even as a human, we have several decisions that we can make for a particular problem. And we don't always necessarily implement all the solutions. We make a particular decision, and then we implement it. It's the same thing with reinforcement learning. So it has several solutions based on the several combinations of states and actions, and then it chooses a particular decision to implement. And again, it calculates the probabilistic inference on the decision making. For example, as I mentioned in AlphaGo, so in a specific game board, Go, so this is the next move it has to make. And it also has a million other moves suggested through reinforcement learning. What it does is it picks the one, like for example, the 99.8% winning rate. And that's the decision that it chooses.
So you're also saying that reinforcement learning can be the learning itself, the machine learning or AI can be reinforced to have gut instinct. Which
yes,
is the human
it can be.
equivalent
That's
of
like
that.
even in this case, I was telling that this particular 24K competition entries has produced around 96 years of simulations of data. So they have created 96 years worth of data to predict how we can solve this problem. And a human probably may not even be able to do it in a lifetime. And that's where the reinforcement learning helps. And similarly, like if you're talking about like counting stars in a galaxy. So if we take a supercomputer and run a high-performance computing algorithm and do a parallel computing on it, it may take some time to do it. But if you apply a reinforcement learning, it can perform so many calculations, and it trains it, and then it can produce the number accurately, closer to the probabilistic inference. How does it compete?
GAN networks are almost the exact same thing, right? So
So the GAN networks are basically,
they're just adversarial networks against what you.
so GAN networks is a very good example. It's a basically the adversarial networks are like we have implemented for genomics and the drug discovery. And the drug discovery basically, if we have to even find a new compound for manufacturing a drug or a combination of the compound, so we can leverage the GANs for that. And that will produce the right outcomes for the drug discovery, which expedites the process, because normally if you have to go through that, it will take a while to come to a conclusion. And that's when the FDA is spending so much of amount on the investigational drugs or experimental drugs. So these experimental drugs are ready, or they're not in the market yet, because FDA has not approved, because it needs to have certain amount of population of people where we can train this and then release into the market. But I think you might have, as you might have heard about the Right to Try Act, which was just approved recently, that helps to empower the people with a right to live. Because if somebody is waiting for a drug to be released in the market, and it's going to be released only after a few years, and this person may not have time for that. But again, it's an experimental drug. It can benefit or it cannot benefit. So that's where we can apply the machine learning technique to do the drug discovery and understand the compound and then apply it. It can help to discover the drug much quicker and efficiently than through the regular clinical trials and different approaches in the healthcare industry. So reinforcement learning is about to revolutionize the healthcare industry as well. So that's where, to answer your question, GANs can be very powerful to revolutionize the healthcare industry as well. I'm not going to go into the details of the equation for now. It's going to take some time. So, I'm writing a book on deep reinforcement learning in PyTorch, which will be released in a few months, hopefully, where I might be able to provide more equations and breakdown of how it can be applied, and with actual demos of different industries and different algorithms. But for now, I'm just going to talk about the Markov decision processes. Again, DeepMind has set up another gaming environment called Atari. So Atari is a gaming environment, and there are a number of reinforcement learning algorithms that have been implemented here, leveraging deep Q networks and policy gradients and actor critic methods, on policy, off policy, Markov decision programs, and dynamic programming. So basically, as I mentioned, it does not require the historical data sets, so that's where it becomes a model-free reinforcement machine learning algorithm. So it doesn't need to have a machine learning model built to train and label the data and then actually run your algorithm. It basically works without having to have any historical data. So also, as you might be aware of, OpenAI is basically another company. Also has set up something called OpenAI Gym, where they're training the robots to achieve this AGI through evolutionary algorithms. And but this one I'm more focusing on the Markov decision processes. So if we take here, so as I mentioned, like if you're on Mars, it has an infinite horizon because we are in a agent-bound environment. It's an infinite horizon because That's when we need to make a decision on a landscape like that. And how do we do that? So basically, it is achieved through SAPR. So basically, there is a finite state space, and there is a finite action, and there is a reward for each iteration. And through the environment, as the robotic agent moves through, it finds the decisions that it needs to make for the actions to be performed. So that's basically the discount factor. So it goes through episodic iterations. We train the agent on an episodic iteration to give that kind of an outcome to reach to an action. The action is the decision, basically. So the states and actions are pairs. And for each state, there is a corresponding action. So how do we achieve reach a particular goal is based on the reward for each iteration. And then there is a discount factor for a reward. And then finally, we achieve the action, and that is the decision. That's how human does it, and that's what we're trying to do is get closer to human brain and get closer to the AGI. So again, there is another environment that has been created called Atari Zoo. So Atari Zoo is basically pre-trained reinforcement learning models where there is a number of algorithms available. Just as an example, Uber Eats recommendations applies the reinforcement learning in our day-to-day life. So it basically provides the recommendations through reinforcement learning. And there are also Montezuma's Ridge or Pitfall are the few other Atari gaming environment agents that are also trained on the reinforcement learning. So as I was talking about OpenAI Gym earlier, OpenAI Gym basically takes the evolutionary algorithms. Evolutionary algorithms are completely bio-inspired. They just take the way, like if you're taking a bee colony, for example. Bee colony has a specific way of doing the things. They find the food. So it's based on the nature. So those are the bio-inspired algorithms, and that's what has evolved into evolutionary algorithms. So OpenAI applies these type of evolutionary algorithms, and they take different type of data from the representations of different combinations, and it produces this entire Atari Zoo can be reproduced, and it can be run. And there's also Sequest, is another console from Atari, and that can be run as well. And you may be wondering, how does it help in daily life? Just as I mentioned, Uber Eats is a very simple outcome of Atari Zoo. So several recommendation systems are fueled by reinforcement learning systems. And it could be applied to any other areas of, like Uber is right now implementing autonomous cars powered by reinforcement learning. They not only calculate the optimal distance from point A to point B, they also try to efficiently drive it, because there are different techniques like radar and LIDAR. LIDAR is a light range technique. So it basically detects the light in the surrounding areas, and it finds that there is an object moving. Once it throws the light, it finds here is where the object, and then it can evade from the object and move away from that so that it can avoid any type of collisions on the road. So that's another example of LIDAR sensors have already been deployed, and some of the cars like Tesla and Uber is implementing on their autonomous cars, and several other cars like Ford and other companies are also implementing autonomous algorithms on the vehicles to further advance the research on reinforcement learning. So now we are talking about these reinforcement learning algorithms and a distributed cloud computing environments. It's not just that we run these on a standalone machines. As I mentioned, that it can be run on clusters of computers, on supercomputers like Palladius, or it could be any other supercomputer for exascale. Exascale computing is another example where we can run this reinforcement learning. So here I'm going to just discuss about some of the tools, and you can just quickly go through these tools, and we will leave the session open for questions. This is Intel's optimized deep learning, machine learning frameworks, where we can implement a lot of reinforcement learning through Apache Spark and several other techniques. And this is from NVIDIA, deep learning frameworks with DGX. So basically, it has the GPUs, and it can accelerate the speed of the reinforcement learning. And this is, again, Power AI platform from IBM. And it also has several frameworks and neural building blocks, how to build the neural networks, how to train the machine learning algorithms, and all that stuff. And then how do we scale it to the cloud? So that's another example of Power AI from IBM. And this is H2O, another framework for performing and applying any of these techniques. And basically, it takes the native support of the GPU, and it basically accelerates the training on the deep neural networks by 100 times faster than Intel CPUs. And this is Amazon's Apache MXNet AWS framework. Again, it has a number of tools, like starting from the most ancient programming language, C, all the way to the advanced R and Python. I mean, it runs on Linux machine, it runs on Android, or it can also run on Mac OS, as well as on Windows. So I'm going to release these slides later for public reading, so that I also added several tutorials and assignments and competitions from MIT deep learning-based reinforcement learning that can be applied to any company. If your organization is basically looking to build a data science team, or you're planning to train your data scientists on the most advanced reinforcement learning, that could be helpful. And it helps for you to gear your data science team. Or if you already have a data science team, you can also help them to advance the team with the most promising landscape of reinforcement learning. So that's where this can be helpful. Or if you're into research field, some of the references can help to add and further advance the research. It just gives back for the research community. So with that said, I'm going to open this up for any questions you may have. Yes, please. The name? Yeah, it's just going to be...
The name for the new book you are going to publish in the next month.
Yes, it's Deep Reinforcement Learning in PyTorch. Deep Reinforcement Learning Cookbook in PyTorch.
Thank you.
Hi, Dr. GP. Thank you. Wanted to ask about, I feel like increasingly, as AI just gets more and more trendy, products that are marketed to businesses, are advertised as using artificial intelligence, and really very few of them, from my experience, get anywhere near this level of artificial intelligence. Most of it's very rules-based still. I'm wondering if, in your experience, you have seen companies that are successfully, obviously when you have a large team of developers and you can spend time with hiring data scientists and a team to do that, you can leverage some of the tools that you've highlighted. I'm just curious if you've seen any really successful low-code environments or applications like that for smaller businesses.
So you're asking any companies that have been successful with rule-based systems?
Well, any companies that are helping leverage these models, the deep reinforcement learning.
Deep reinforcement learning?
In
so
low-code
several
environments.
Healthcare companies already started implementing this. There are a number of companies that are implementing on the healthcare industry. And lot of autonomous car industries are also implementing it. For example, as I mentioned, Uber. And Ford also is looking into it. Tesla has some LiDAR sensors where they're specifically trying to implement that. And then I think NASA already has implemented or already in the process of implementing it. I think they're building the solar sails, laser sails that can probably compete with the speed of light as next generation spacecraft expeditions. They're leveraging all of these reinforcement learning algorithms and applying to it. And that's where they can actually benefit it because they're going to find these exoplanets or wherever they have to go to Mars, they need all these reinforcement learning algorithms. So it has been heavily implemented in space exploration industry as well. And also, surprisingly, it also has been implemented for financial industry as well. That kind of predicts the advanced financial forecast. So if there are any financial corporations and they want to know how does their chart look like or what is their profitability and whether they need to continue to manufacture at plant A versus plant B, it tells if they continue to manufacture with this combination, this is what your profit is going to look like down the road. And then if you're going to continue to produce from different plants, then you have different outcomes of the financial projections. So it has been implemented in financial industry as well. And the other industry is supply chain management, where it has been extensively implemented. For example, there is a software called SAP. And so there is a heavy supply chain management. And it can actually calculate the demand and supply equation. Because before people start manufacturing things, they need to have a demand forecast equation as to exactly what is their demand is going to look like. And then they have to build their advanced planning optimization techniques to manufacture. And reinforcement learning has been implemented to address that. There's actually a separate ebook I wrote for SAP where I provided those examples of demand distribution calculations on the SAP. If you're interested, please email me. I can share with you later.
Well, let's give Dr. GP a round of applause.
Thank you very much for all of you.
I'm sure that Dr. GP will be around during our networking breaks and lunches, so if you have any further questions, please don't hesitate to find him. I did also want to mention briefly, I'm sure you saw in your conference guide that our keynote about smart home technology, it was supposed to be scheduled for this morning. We have had to move